Right now, you're trapped in a cosmic prison so vast that most people never even realize the bars exist. Despite being our closest major galaxy, Andromeda might as well be on the other side of infinity. The real reason we can't reach it isn't just about distance or technology, it's about the fundamental nature of space, time, and reality itself. The universe itself is working against us. What you're about to learn will fundamentally change how you see every star in the night sky and humanity's place among them. And one quick question. If you could instantly master any scientific field, which one would you choose? And the reason why? Let me know in the comments. I always pin the most creative answer. Now let's begin. The Andromeda Galaxy sits 2.54 million light-years away from us. To put that in perspective, if you could travel at the speed of light, the fastest possible speed in the universe, it would still take you over 2.5 million years to reach our galactic neighbor. That's longer than humans have existed as a species. It's longer than complex life has existed on Earth. When the light we see from Andromeda tonight began its journey, our earliest human ancestors were just learning to use stone tools. But the speed of light isn't just fast, it's the cosmic speed limit. Einstein's special theory of relativity, confirmed by over a century of experiments, tells us that nothing with mass can ever reach light speed. As you approach the speed of light, your mass effectively becomes infinite, requiring infinite energy to accelerate further. It's not just a technological limitation, it's a fundamental law of physics that governs how reality works. This means that even our most optimistic dreams of interstellar travel fall laughably short of what we'd need to reach Andromeda. The fastest spacecraft humans have ever built, Voyager 1, is currently traveling at about 38,000 miles per hour. At that speed, it would take roughly 17 billion years to reach Andromeda, longer than the universe has existed. Even if we could somehow build a spacecraft traveling at 10% the speed of light, the journey would still take 25 million years. But the challenges go far deeper than just speed and distance. The space between galaxies isn't empty, it's filled with what astronomers call the intergalactic medium. This incredibly thin soup of gas and dark matter might seem negligible, but at the speeds required for intergalactic travel, even individual atoms become deadly projectiles. A spacecraft traveling at significant fractions of light speed would be bombarded by cosmic radiation so intense it would be vaporized within hours. The Hubble Space Telescope and other observatories have revealed that the space between galaxies is also expanding. This isn't just galaxies moving apart through space. Space itself is stretching, carrying galaxies along with it. The expansion of the universe means that Andromeda and the Milky Way are actually approaching each other due to their mutual gravitational attraction, but most other galaxies are racing away from us at ever-increasing speeds. This cosmic expansion, driven by the mysterious force we call dark energy, creates what physicists call the cosmological horizon. Beyond a certain distance, galaxies are receding from us faster than light can travel between them. We can see these distant galaxies because their light was emitted when they were closer, but we can never reach them because space itself is expanding faster than we could ever travel. Recent observations from the James Webb Space Telescope have confirmed that this expansion is accelerating. Dark energy, which makes up about 68% of the universe, is pushing space apart at an ever-increasing rate. This means that the observable universe, the sphere of space from which light has had time to reach us, is actually shrinking in terms of what we can potentially visit. The energy requirements for intergalactic travel reveal another insurmountable barrier. To accelerate even a small spacecraft to a significant fraction of light speed would require more energy than our entire civilization produces. The most efficient rocket fuel theoretically possible, matter, antimatter, annihilation, would still require fuel masses many times larger than the spacecraft itself. We're not talking about engineering challenges, we're talking about physical impossibilities. But perhaps the most profound barrier to reaching Andromeda is time itself. Even if we could somehow overcome the speed and energy limitations, the journey would unfold over timescales that dwarf human civilization. The people who launched such a mission would be long dead before it arrived. Their entire civilization might have risen and fallen multiple times. The very species that sent the spacecraft might have evolved into something unrecognizable. If these cosmic realities are already reshaping how you think about our place in the universe, make sure to hit that subscribe button and give this video a thumbs up. We're just scratching the surface of why Andromeda remains forever beyond our reach. The biological challenges of intergalactic travel add another layer of impossibility. Human bodies are exquisitely adapted for life on Earth. Our gravity, our atmosphere, our magnetic field. The radiation environment of intergalactic space would be lethal to any known form of life. Cosmic rays, high-energy particles from distant supernovae and black holes would tear through DNA and destroy cellular structures. No amount of shielding could protect travelers on such a journey. Even if we could somehow solve the radiation problem, the psychological challenges would be overwhelming. Imagine being trapped in a spacecraft for millions of years, knowing that everyone you've ever known is dead, that your home planet might not even exist anymore. The isolation would be absolute, no real-time communication with Earth, no possibility of rescue, no hope of return. It's a form of exile that goes beyond anything humans have ever experienced. The technological challenges are equally daunting. Any spacecraft capable of intergalactic travel would need to be completely self-sufficient for millions of years. Every component would need to function perfectly without maintenance or replacement. The spacecraft would need to carry its own manufacturing capabilities, its own ecosystem, its own civilization. We're talking about building a world that could survive longer than complex life has existed on Earth. But there's an even deeper problem lurking in the physics of space and time. Einstein's general theory of relativity tells us that space and time are woven together into a four-dimensional fabric called spacetime. Massive objects like galaxies warp this fabric, creating gravitational fields that affect the flow of time itself. As you travel deeper into gravitational wells or approach high speeds, time dilation effects become significant. This time dilation effect means that travelers to Andromeda would experience time differently than those left behind on Earth. At speeds approaching the speed of light, time would slow down dramatically for the travelers. They might experience the journey as taking only thousands of years, while millions of years pass on Earth. They would arrive at Andromeda to find that human civilization had either evolved beyond recognition or gone extinct entirely. It's not just a journey through space, it's a one-way trip to the future with no possibility of return. The concept of simultaneity breaks down over intergalactic distances. What we consider now on Earth has no meaningful connection to now in Andromeda. Events that appear simultaneous from one reference frame happen at different times from another. This isn't just philosophical speculation, it's a fundamental aspect of how space-time works. The very notion of traveling to Andromeda assumes a shared present that doesn't actually exist. But let's step back and consider something even more fundamental. If reaching our nearest planetary neighbor is already pushing the limits of human capability, and I explored just how challenging that is in my video, "This is why it's impossible for us to reach Mars," then the gulf between planets and galaxies represents a barrier of an entirely different magnitude. We're not talking about scaling up our technology, we're talking about transcending the physical laws that govern our universe. The Fermi Paradox takes on new meaning when we consider these intergalactic barriers. If intelligent civilizations are common in the universe, why haven't we detected any signs of them? One possible answer is that the universe has built-in isolation mechanisms. The vast distances between galaxies, the expansion of space, and the finite speed of light create cosmic islands that can never interact. Each galaxy might be teeming with life, but they're all forever trapped in their own gravitational wells. Recent studies of galaxy formation and evolution have revealed another barrier to intergalactic travel, the cosmic web. Galaxies aren't randomly distributed through space. They're organized along vast filaments of dark matter with enormous voids between them. These voids, spanning hundreds of millions of light-years, contain almost no matter or energy. A spacecraft crossing such a void would be more isolated than anything we can imagine, with no possibility of refueling or finding resources. The dark matter that makes up about 27% of the universe adds another layer of mystery to intergalactic travel. We don't know what dark matter is, but we know it affects the motion of galaxies and the structure of space itself. Any spacecraft traveling between galaxies would be moving through an invisible sea of dark matter, subject to gravitational effects we don't fully understand. It's like trying to navigate an ocean where most of the water is invisible. The quantum mechanical nature of reality presents perhaps the strangest barrier to intergalactic travel. At the smallest scales, the universe operates according to quantum mechanics, where particles exist in superpositions of states and the act of observation affects reality. Some physicists have proposed that consciousness itself might be fundamentally limited to local regions of space, unable to maintain coherence across intergalactic distances. The vacuum of intergalactic space isn't truly empty. It seethes with quantum fluctuations, virtual particles popping into and out of existence. These fluctuations, while individually tiny, could have cumulative effects on any spacecraft traveling for millions of years. The Casimir effect demonstrates that even empty space exerts measurable forces. Over intergalactic distances, these quantum effects could destabilize any technology we might develop. Recent observations from the Event Horizon Telescope and gravitational wave detectors like LIGO have revealed the violent nature of the universe at large scales. Black holes merge, sending ripples through spacetime. Neutron stars collide, creating bursts of gamma rays that can sterilize entire regions of space. The journey to Andromeda would take any spacecraft through billions of years' worth of cosmic catastrophes, any one of which could destroy it instantly. The thermodynamic challenges of intergalactic travel are equally daunting. The second law of thermodynamics tells us that entropy always increases in isolated systems. A spacecraft traveling for millions of years would gradually degrade, its organized structures breaking down into disorder. No amount of maintenance could prevent this eventual decay. The universe itself conspires against the kind of long-term order required for intergalactic journeys. But perhaps the most profound barrier is the nature of information itself. Information can't travel faster than light, which means that any civilization attempting intergalactic travel would fragment into isolated pockets that could never communicate. The travelers to Andromeda would become a separate branch of humanity, forever cut off from their origins. It's not just physical travel that's impossible, it's the maintenance of any coherent civilization across such distances. The latest research in cosmology suggests that the universe might be infinite in extent. If this is true, then somewhere in that infinite expanse, there are exact copies of our galaxy, our planet, even ourselves. But these copies are so far away that we can never reach them or even observe them. The universe might be full of versions of humanity that will never know of each other's existence. The anthropic principle offers another perspective on why we can't reach Andromeda. We exist in a universe with physical laws that allow for the development of life and consciousness, but those same laws might necessarily limit us to our cosmic neighborhood. A universe where intergalactic travel was easy might be one where stable galaxies couldn't form or where life couldn't evolve. Our isolation might be the price we pay for existing at all. Dark energy, the mysterious force accelerating the universe's expansion, ensures that this isolation will only increase with time. In the far future, the expansion of space will carry all other galaxies beyond our observable horizon. Future civilizations will see a universe containing only their own galaxy, with no evidence that others ever existed. The cosmic loneliness we feel now is nothing compared to the absolute isolation that awaits. The multiverse hypothesis adds yet another layer to our cosmic isolation. If our universe is just one of countless others, each with different physical laws, then we're not just isolated from other galaxies, we're isolated from other realities. The barriers between universes, if they exist, would be even more absolute than those between galaxies. We might be surrounded by infinite variations of existence that we can never access or even detect. Recent advances in quantum computing and information theory have revealed fundamental limits on computation and information processing. These limits suggest that even if we could somehow send robotic probes to Andromeda, they would face information theoretic barriers to maintaining coherent operation over such vast timescales. The probe's artificial intelligence would degrade, its memories would corrupt, its purpose would be lost to entropy. The philosophical implications are staggering. If we can never reach Andromeda, what does that mean for humanity's cosmic ambitions? Are we forever trapped in our local group of galaxies, destined to watch the rest of the universe recede beyond our reach? Or is this limitation actually a gift, forcing us to find meaning and purpose within our cosmic neighborhood rather than in endless expansion? The energy density of intergalactic space presents another fundamental barrier that recent observations have only made clearer. The space between galaxies contains roughly 1 atom per cubic meter, a vacuum more perfect than anything we can create in laboratories. But at the speeds required for intergalactic travel, even this incredibly thin medium becomes a wall. Each atom would hit a spacecraft with the energy of a particle in a cosmic ray shower, gradually eroding any material we could possibly build. The cosmic microwave background radiation, that faint afterglow of the Big Bang discovered by Arno Penzias and Robert Wilson in 1964, fills all of space with photons at a temperature of 2.7 Kelvin. For a spacecraft traveling at relativistic speeds toward Andromeda, these harmless microwave photons would be blue-shifted into deadly gamma rays. The faster you go, the more lethal the universe becomes. It's as if space itself resists our attempts to cross it. Recent data from the Planck satellite has mapped this radiation with unprecedented precision, revealing subtle fluctuations that tell us about the structure of space-time itself. These measurements confirm that we live in a universe governed by physical laws that make intergalactic travel not just difficult, but fundamentally impossible for beings like us. The universe has speed limits, energy barriers, and temporal gulfs that no amount of technology can overcome. The gravitational landscape between galaxies adds another layer of impossibility. Dark matter halos extend far beyond the visible portions of galaxies, creating gravitational fields that would affect any spacecraft's trajectory over millions of years. The three-body problem, the mathematical challenge of predicting motion under the influence of multiple gravitational sources, becomes infinitely more complex when dealing with the gravitational influences of billions of stars and dark matter clumps. Computer simulations of intergalactic trajectories reveal chaotic dynamics that make long-term navigation impossible. Tiny uncertainties in initial conditions amplify over time, leading to completely unpredictable outcomes. A spacecraft aimed at Andromeda could end up anywhere within millions of light-years of its target, lost in the cosmic void with no way to correct its course. The universe is not just vast, it's mathematically intractable. The latest observations from gravitational wave detectors have revealed that space-time itself is constantly rippling with waves from distant cosmic events. These waves, predicted by Einstein but only recently detected, stretch and compress space as they pass. Over intergalactic distances, these constant distortions would accumulate, making precise navigation impossible. It's like trying to sail across an ocean where the very fabric of water is constantly changing. But there's an even deeper problem rooted in quantum mechanics. The uncertainty principle tells us that we can never know both the position and momentum of a particle with perfect precision. Over intergalactic distances and timescales, these quantum uncertainties compound into macroscopic effects. A spacecraft's trajectory would become fundamentally unpredictable, not because of technological limitations, but because of the basic nature of reality. The vacuum catastrophe, the enormous discrepancy between the predicted and observed energy density of empty space, hints at physics we don't yet understand. If our theories are wrong about something as fundamental as the vacuum of space, how can we hope to predict what would happen to matter and energy over intergalactic journeys? We might be missing fundamental aspects of reality that make such travel impossible in ways we haven't even imagined. Recent studies of ultra-high energy cosmic rays have revealed particles with energies that shouldn't be possible given our understanding of physics. These particles, accelerated by unknown mechanisms to speeds incredibly close to the speed of light, lose energy through interactions with the cosmic microwave background. This GZK cutoff, named after Grayson, Zatsepin, and Kuzmin, who predicted it, means that even particles traveling at the highest possible speeds can't cross intergalactic distances without losing most of their energy. The holographic principle, emerging from studies of black hole physics, suggests that the information content of any region of space is limited by its surface area rather than its volume. This profound insight implies fundamental limits on how much information can be transmitted across intergalactic distances. The very fabric of spacetime might prevent the kind of complex information transfer required for meaningful intergalactic travel or communication. Time itself becomes strange over intergalactic distances. The universe is 13.8 billion years old, but due to cosmic expansion, the most distant galaxies we can see are now over 46 billion light-years away. The light from Andromeda shows us the galaxy as it was 2.5 million years ago. If we could somehow instantly teleport there, we'd arrive in a galaxy that has evolved for millions of years beyond what we observe. The present is a local phenomenon that doesn't extend across intergalactic space. The thermodynamic arrow of time presents another barrier. Entropy increases in isolated systems, and any spacecraft traveling between galaxies would be the most isolated system imaginable. Over millions of years, every organized structure would degrade, every memory would corrupt, every purpose would be forgotten. The travelers would arrive as cosmic debris, their original mission lost to the inexorable march of entropy. But perhaps the most haunting barrier is the silence. Despite decades of searching, we've detected no signals from other civilizations, no evidence of intergalactic travel, no cosmic engineering projects spanning the void between galaxies. The Great Silence might be telling us something profound, that intelligence is forever trapped within its home galaxy, isolated by physics itself from the wider universe. The latest data from the Dark Energy Survey has revealed that the universe's expansion is not just accelerating, it might be accelerating at an increasing rate. This phantom energy scenario would lead to a big rip, where the expansion of space eventually tears apart all structures, from galaxy clusters down to atoms themselves. In such a universe, the window for intergalactic travel might be closing, making our isolation not just current, but eternal. Quantum entanglement, often misunderstood as a way to communicate faster than light, actually reinforces our cosmic isolation. While entangled particles do share instantaneous correlations, no information can be transmitted through entanglement alone. The universe has built-in safeguards against faster-than-light communication, ensuring that each galaxy remains an island of causality in an ocean of spacetime. The computational limits of the universe itself might prevent intergalactic travel. Some physicists propose that spacetime has a fundamental granularity, a smallest possible scale below which the concept of space and time breaks down. This Planck scale structure might make it impossible to maintain coherent structures or information patterns over intergalactic distances. The universe might be pixelated in a way that prevents smooth travel between its largest structures. Recent observations of fast radio bursts, mysterious pulses of radio energy from distant galaxies, have revealed the extreme environments of intergalactic space. These bursts, lasting only milliseconds but releasing as much energy as the Sun emits in days, demonstrate the violent and unpredictable nature of the cosmos. Any spacecraft would need to survive not just the known hazards, but unknown phenomena that we're only beginning to discover. The discovery of dark flow adds another mysterious barrier to our understanding of intergalactic travel. Some galaxy clusters appear to be moving in a common direction, pulled by gravitational forces from beyond the observable universe. This suggests that the universe we can see is just a tiny fraction of a much larger structure, with gravitational influences we can never map or understand. Trying to navigate between galaxies while unknown forces pull from beyond the cosmic horizon would be like sailing without knowing about continents beyond the horizon. String theory, our best attempt at a theory of quantum gravity, suggests that space might have extra dimensions beyond the three we experience. These dimensions could be compactified, rolled up so small we can't detect them, or they could be large but inaccessible to ordinary matter. If extra dimensions exist, the true geometry of intergalactic space might be far more complex than we imagine, with shortcuts that we can never access or barriers we can't perceive. The false vacuum hypothesis presents perhaps the most terrifying barrier of all. Our universe might exist in a metastable state, like a ball perched on a shelf rather than on the floor. If this is true, then somewhere in the universe, space itself could spontaneously transition to a lower energy state, creating a bubble of true vacuum that expands at the speed of light, destroying everything in its path. Intergalactic travelers could be annihilated by a wave of cosmic destruction that they could never see coming. Recent measurements of the Hubble constant, the rate at which the universe is expanding, have revealed a troubling discrepancy. Different methods give different values, suggesting that we're missing something fundamental about cosmic expansion. This Hubble tension might indicate new physics that makes intergalactic travel even more impossible than our current theories suggest. The universe might be playing by rules we haven't discovered yet. The cosmic neutrino background, a sea of neutrinos left over from the Big Bang, fills all of space with ghostly particles that barely interact with matter. For normal travel, these neutrinos are irrelevant, but at the extreme energies required for intergalactic travel, neutrino interactions could become significant, creating drag forces we've never had to consider. The universe is filled with invisible obstacles that only reveal themselves at the highest speeds. Magnetic fields thread through intergalactic space, invisible but influential. These fields, generated by ancient cosmic processes we don't fully understand, could deflect charged particles and affect the trajectory of any spacecraft using advanced propulsion. Recent observations have revealed magnetic fields in cosmic voids where we expected none, suggesting that even empty space has structure that could interfere with intergalactic travel. The possibility of primordial black holes formed in the early universe rather than from dying stars, adds another hazard to intergalactic space. These invisible gravitational traps could be scattered throughout the void, impossible to detect until it's too late. A spacecraft could be captured and destroyed by a black hole that's been lurking in empty space for billions of years. But beyond all these physical barriers lies a deeper question about the nature of consciousness and identity. Even if we could somehow send humans to Andromeda, would they still be human when they arrived? Millions of years of isolation, adaptation, and evolution would transform them into something unrecognizable. The barrier isn't just about reaching Andromeda, it's about maintaining any meaningful connection to what we are. The simulation hypothesis offers a different perspective on our cosmic isolation. If our universe is a simulation, then the barriers to intergalactic travel might be computational limits rather than physical ones. The vast empty spaces between galaxies could be regions where the simulation saves processing power by not rendering details. Our inability to reach Andromeda might be built into the very code of reality. Recent advances in quantum biology have revealed that life itself might be fundamentally local. Quantum processes in living cells, from photosynthesis to neural activity, might depend on local conditions in ways we don't yet understand. Life that evolved on Earth might be physically unable to survive the different quantum environment of intergalactic space or another galaxy. We might be more tied to our cosmic neighborhood than we realize. The fine-tuning problem in cosmology suggests that the physical constants of our universe are precisely calibrated for the existence of stars, planets, and life. But this same fine-tuning might necessarily create the barriers that keep us isolated. A universe where intergalactic travel was easy might be one where galaxies couldn't form or life couldn't evolve. Our cosmic prison might be the price of our existence. Observations of galaxy collisions provide a sobering preview of Andromeda's approach. The Milky Way and Andromeda are gravitationally bound and will collide in about 4.5 billion years. But this collision will take hundreds of millions of years to unfold, with the two galaxies passing through each other multiple times before merging. Even when galaxies collide, the vast distances between stars mean that stellar collisions are extremely rare. Space is so empty that even galactic collisions are mostly empty space passing through empty space. The concept of cosmic inflation, the exponential expansion of space in the early universe, helps explain why the universe is so uniform on large scales, but also why galaxies are so isolated. Inflation took quantum fluctuations and stretched them to cosmic scales, creating the seeds of galaxies while also ensuring they would be separated by vast voids. The same process that created galaxies also imprisoned them. Dark energy's nature remains one of the biggest mysteries in physics. It could be a cosmological constant, an intrinsic property of space itself. Or it could be a dynamic field that changes over time. If dark energy is increasing, as some models suggest, then the universe's expansion will accelerate until galaxies are ripped apart in a Big Rip scenario. The window for any kind of intergalactic travel or communication might be closing. The anthropic principle suggests we shouldn't be surprised by our cosmic isolation. In a multiverse of possible universes, we necessarily find ourselves in one that allows for our existence. Universes where intergalactic travel is possible might have different physical laws that prevent the formation of stable stars or complex chemistry. We observe cosmic isolation because only isolated observers can exist. Recent studies of gamma-ray bursts, the most energetic explosions in the universe, reveal another hazard of intergalactic space. These bursts, caused by collapsing stars or merging neutron stars, can briefly outshine entire galaxies and would be lethal to any life within thousands of light years. Over the millions of years required for intergalactic travel, a spacecraft would inevitably encounter multiple gamma-ray bursts, each capable of destroying all life aboard. The topology of space itself might prevent intergalactic travel. While space appears flat on large scales, it could have a complex topology with multiple connected regions. Some theories suggest that space might be like a hall of mirrors, where traveling far enough in one direction brings you back to where you started. In such a universe, there might be no path to Andromeda that doesn't lead back to the Milky Way. The quantum Zeno effect presents another bizarre barrier to intergalactic travel that emerges from the fundamental nature of reality. This effect shows that observing a quantum system frequently enough can freeze its evolution. Over intergalactic distances, the constant interaction of a spacecraft with cosmic radiation and quantum fields might create a similar effect, preventing the coherent evolution of any complex system. The universe might literally prevent change over such vast scales. Recent discoveries about the nature of time itself challenge our assumptions about intergalactic journeys. Time might not be fundamental, but could emerge from more basic quantum processes. If time is emergent, then over intergalactic distances, the very notion of a journey with a beginning and end might break down. Travelers might find themselves in regions where time itself behaves differently, making the concept of arrival meaningless. The cosmic web structure reveals that most of the universe's volume is empty void. These voids aren't just empty, they're expanding faster than the denser regions where galaxies reside. A spacecraft trying to cross a void would be fighting against the expansion of space itself, like trying to swim upstream in a river that gets faster the farther you go. The universe's large-scale structure actively resists traversal. Observations from the Atacama Large Millimeter Array have revealed complex organic molecules in distant galaxies, suggesting that the chemistry of life might be universal. But this same universality might mean that life is forever trapped in the environments where it evolves. The specific conditions that allow for complex chemistry, temperature, pressure, radiation levels, might be so finely balanced that leaving one's home galaxy is biochemically impossible. The information paradox of black holes, partially resolved by Stephen Hawking's work on black hole evaporation, suggests that information can be preserved but scrambled beyond recognition. Over intergalactic distances, similar scrambling might occur to any information pattern, including the memories and purposes of travelers. The journey itself might erase the reason for traveling, leaving arrivals with no memory of why they came. Gravitational lensing observations have revealed that dark matter forms complex structures throughout intergalactic space. These invisible rivers and clumps of dark matter could create gravitational mazes that make navigation impossible. A spacecraft might find itself trapped in dark matter currents that carry it far from its intended destination, lost in an invisible landscape we can't map. The possibility of cosmic strings, theoretical defects in spacetime left over from the early universe, adds another exotic barrier. These strings, thinner than an atom but potentially spanning millions of light years, would have gravitational fields that could slice through any material. Encountering a cosmic string during intergalactic travel would be instantly catastrophic, and we have no way to detect them in advance. Recent studies of quasar absorption lines have revealed the intergalactic medium's complex structure. Clouds of gas, shock-heated regions, and metal-enriched outflows from ancient galaxies create a turbulent environment between galaxies. This isn't empty space, but a dynamic, evolving medium that would buffet any spacecraft with forces we're only beginning to understand. The holographic principle suggests that all the information in a volume of space can be encoded on its boundary. This might mean that traveling through space is actually moving across a two-dimensional surface, with the illusion of three dimensions. The true geometry of intergalactic travel might be fundamentally different from our intuitive understanding, with barriers that exist in the holographic encoding rather than in apparent space. Quantum decoherence, the process by which quantum systems lose their coherent properties through interaction with the environment, would be extreme over intergalactic distances. Any quantum technologies required for advanced spacecraft would face decoherence times measured in nanoseconds. The quantum advantages that might make intergalactic travel possible are precisely what the universe destroys over such scales. The measurement problem in quantum mechanics takes on new significance for intergalactic travel. If consciousness plays a role in quantum measurement, as some interpretations suggest, then the extreme isolation of intergalactic space might affect the fundamental nature of reality for travelers. They might find themselves in a quantum limbo, where the normal rules of physics no longer apply in familiar ways. Recent observations of ultra-diffuse galaxies have revealed that some galaxies are so spread out they're barely held together by gravity. This suggests that the universe tends toward dispersion rather than connection. The same forces that create ultra-diffuse galaxies might act on any structure attempting intergalactic travel, gradually dispersing it across space until nothing coherent remains. The cosmic censorship hypothesis proposed by Roger Penrose suggests that the universe prevents naked singularities, points where physics breaks down, from being observed. A similar principle might apply to intergalactic travel. The universe might have built-in mechanisms that prevent any observation or interaction across such vast scales, maintaining cosmic censorship of distant regions. Dark matter's properties remain almost completely unknown despite decades of searches. It could be made of particles that interact with normal matter in ways we haven't discovered. Over intergalactic distances, these unknown interactions could accumulate, creating drag forces, navigation errors, or even more exotic effects that make travel impossible. We're trying to cross an ocean whose water we can't see or understand. The possibility of mirror matter, a theoretical form of matter that interacts with ordinary matter only through gravity, could mean that intergalactic space is full of invisible obstacles. Entire mirror galaxies could exist in the same space as visible galaxies, creating gravitational fields that would make navigation chaotic. The universe might be twice as crowded as we think, with half of it completely invisible. Observations of the cosmic dawn, the era when the first stars formed, show that the universe underwent dramatic changes that we're still trying to understand. The reionization of intergalactic hydrogen, driven by the first stars and galaxies, transformed space from opaque to transparent. Similar phase transitions might still be possible, potentially making intergalactic space suddenly hostile to any travelers caught in the change. The ekpyrotic universe model suggests that our universe might cyclically collide with parallel branes in higher dimensions. These collisions could send ripples through spacetime that would destroy any structure attempting intergalactic travel. We might live in a universe where periodic cosmic catastrophes make long-distance travel impossible, like trying to sail during unpredictable tsunamis. Quantum tunneling allows particles to pass through barriers they classically couldn't overcome. But over intergalactic distances, quantum tunneling could work against travelers, allowing spacecraft components to spontaneously decay or reconfigure. The same quantum effects that might enable exotic propulsion could also ensure that nothing complex survives the journey. The cosmic coincidence problem, why dark energy and matter density are comparable in the present epoch, might indicate that we live at a special time in cosmic history. Earlier, dark energy was too weak to prevent structure formation. Later, it will be too strong to allow any travel between galaxies. We might exist in a brief window when we can see other galaxies but can never reach them, a cosmic tease that shows us what we can never have. The thermodynamics of information processing reveals another fundamental barrier to intergalactic travel. Landauer's principle states that erasing information generates heat, and any computational system must eventually dissipate energy. Over millions of years, even the most efficient computer systems would need to radiate away enormous amounts of waste heat. In the cold of intergalactic space, this heat would dissipate so slowly that spacecraft systems would overheat and fail long before reaching their destination. Recent research into the arrow of time suggests that entropy might not increase uniformly throughout the universe. Different regions of space might have different thermodynamic arrows, creating zones where cause and effect relationships break down. Intergalactic travelers could find themselves in regions where the future doesn't follow from the past in any predictable way, making navigation and survival impossible. The weak force, one of nature's four fundamental forces, might behave differently over intergalactic distances. This force governs radioactive decay and certain particle interactions. If the weak force's strength varies with cosmic environment, then the radioactive power sources that spacecraft rely on might decay faster or slower than expected, creating energy crises that doom any mission. We assume the laws of physics are constant, but we've only tested them locally. Cosmic voids, the enormous empty regions between galaxy filaments, contain almost no visible matter, but they're still subject to the expansion of space. Recent simulations show that voids expand faster than the average expansion rate of the universe. A spacecraft crossing a void would find the exit receding faster than it approaches, like trying to reach a doorway that moves away from you with every step. The Lyman alpha forest, patterns of absorption lines in the spectra of distant quasars, reveals the complex distribution of hydrogen in intergalactic space. This hydrogen, left over from the Big Bang, forms clouds and filaments that would create drag on any spacecraft. More importantly, these clouds indicate that truly empty space doesn't exist. Every cubic meter of the universe contains matter that would interact with travelers over sufficient time and distance. Observations of gravitational waves from merging black holes have confirmed that spacetime itself can vibrate like a drumhead. Over intergalactic distances, the accumulated effects of billions of years of gravitational waves could create a chaotic spacetime landscape. Trying to maintain a stable trajectory through constantly warped space would be like sailing a perfectly straight line in an ocean during a storm that never ends. The cosmological constant problem, why is dark energy's value so small compared to theoretical predictions, remains unsolved. This suggests our understanding of vacuum energy is fundamentally flawed. If we're wrong about something as basic as empty space, we can't predict what would happen to matter traveling through intergalactic vacuum for millions of years. The errors in our theories might be invisible at small scales, but catastrophic at galactic scales. Recent discoveries of fast blue optical transients, mysterious explosions in distant galaxies, show that the universe produces violent events we don't understand. These explosions, different from supernovae or gamma-ray bursts, remind us that space is full of hazards we haven't catalogued. Intergalactic travelers would face not just known dangers, but unknown phenomena that could destroy them without warning. The cosmic microwave background temperature fluctuations, mapped precisely by the Planck satellite, reveal the universe's structure when it was only 380,000 years old. These primordial patterns determine where galaxies formed and where voids opened up. The universe's structure isn't random, it's been predetermined since the cosmic dawn. The gaps between galaxies might be as fundamental and unchangeable as the galaxies themselves. Supermassive black hole formation remains mysterious. Every large galaxy hosts a black hole millions to billions of times the mass of our Sun, but we don't fully understand how they grew so large. If these black holes produce effects we haven't detected, intergalactic space might be filled with their invisible influence, gravitational waves, magnetic fields, or exotic particles that would affect any travelers. The baryon acoustic oscillations, the cosmic equivalent of sound waves in the early universe, have left imprints on the large-scale structure of the cosmos. These oscillations create a characteristic scale in how galaxies cluster. This fundamental scale might also limit how structures can move through space. Trying to travel against the cosmic grain could encounter resistance built into the universe's basic architecture. Quantum field theory predicts that the vacuum isn't a state of nothingness but the lowest energy state of quantum fields. These fields permeate all of space, and particles are excitations of these fields. Over intergalactic distances, the cumulative effects of traveling through all these quantum fields could be profound. A spacecraft might lose energy to the vacuum itself, bleeding velocity into quantum fluctuations until it comes to rest in the void. The reheating period after cosmic inflation, when the energy of the inflaton field converted into matter and radiation, set the initial conditions for everything in the universe. If different regions reheated differently, intergalactic space might have subtle variations in physical laws that we haven't detected. Travelers crossing into different reheating domains could face changing physics that make survival impossible. Recent observations of tidal streams, stars torn from small galaxies by larger ones, show that gravitational interactions can extend over millions of light years. The Andromeda Galaxy has consumed dozens of smaller galaxies, leaving stellar streams throughout the intergalactic medium. This debris field creates a navigational hazard and reminds us that the space between galaxies is a graveyard of cosmic collisions. The cosmic ray spectrum, the distribution of particle energies in cosmic rays, has features we don't fully understand. The knee and ankle in the spectrum suggest multiple sources and acceleration mechanisms. Some of these cosmic rays might come from intergalactic space itself, implying energetic processes occurring in the voids. Any spacecraft would be bombarded by particles from unknown sources, accumulating damage over millions of years. Magnetic reconnection events, where magnetic field lines break and reconnect, release enormous amounts of energy. These events occur in the Sun's atmosphere and in Earth's magnetosphere, but they might also happen in intergalactic magnetic fields. A spacecraft caught in an intergalactic reconnection event could be subjected to particle acceleration and energy release equivalent to a solar flare, but with no warning and no protection. The vacuum birefringence effect, where strong magnetic fields change the properties of empty space, has been detected around neutron stars. If intergalactic magnetic fields are stronger than we think, they could create optical illusions that make navigation impossible. Travelers might see Andromeda where it isn't, chasing a mirage created by curved light paths through magnetized vacuum. Recent studies of the metallicity of intergalactic gas reveal that it's been enriched by galactic winds and supernova explosions. This means that intergalactic space isn't pristine. It's polluted with heavy elements from billions of years of stellar death. These metals, while trace amounts, could create unexpected chemistry with spacecraft materials over millions of years of exposure. The cosmological lithium problem, the discrepancy between predicted and observed lithium abundance, suggests we're missing something about the early universe or nuclear physics. This missing piece might also affect our understanding of how matter behaves over cosmic timescales. We might be fundamentally wrong about the stability of materials in the extreme environment of intergalactic travel. The Sunyaev-Zeldovich effect, where cosmic microwave background photons gain energy passing through hot gas, reveals vast reservoirs of ionized material between galaxy clusters. This hot intergalactic medium, heated to millions of degrees by gravitational collapse and galactic feedback, would be invisible to optical telescopes but lethal to any spacecraft. Traveling through plasma at such temperatures would be like flying through the sun's corona for millions of years. Primordial magnetic fields potentially generated during cosmic inflation might thread through all of space with strengths we can't yet measure. These fields, twisted and amplified by billions of years of cosmic evolution, could create magnetic mazes that trap charged particles. Any spacecraft using electromagnetic propulsion would find itself fighting against invisible magnetic currents that span the space between galaxies. The cosmic neutrino background, predicted to exist at a temperature of about 1.9 Kelvin, contains neutrinos that decoupled from other matter when the universe was only 1 second old. These relic neutrinos vastly outnumber all the atoms in the universe. While individual neutrinos rarely interact with matter, over intergalactic distances and timescales, their cumulative effects might create a subtle drag that slows all matter attempting to cross the void. Recent observations of circumgalactic media, the halos of gas surrounding galaxies, show that galaxies aren't isolated islands but are connected by streams of infalling and outflowing material. These cosmic rivers of gas could extend well into intergalactic space, creating turbulent regions that would buffet any spacecraft with unpredictable forces. The universe's plumbing system might be far more complex than we imagined. The epoch of reionization, when the first stars ionized hydrogen throughout the universe, fundamentally changed the properties of intergalactic space. But this process might not have been uniform. There could be pockets of neutral hydrogen remaining, creating regions where light propagates differently. Travelers could find themselves in zones where their sensors fail, their communications are blocked, and their navigation systems give contradictory readings. Cosmic strings, if they exist, could create closed time-like curves, paths through space-time that loop back on themselves. A spacecraft encountering such a structure might find itself returning to an earlier point in its journey, trapped in a temporal loop. The universe might contain temporal traps that make forward progress impossible, regions where the distinction between past and future breaks down. The cosmological no-hair theorem suggests that the universe loses information about initial conditions through expansion and entropy. This erasure of information might extend to any complex structures attempting intergalactic travel. The spacecraft, its crew, and its purpose might be information that the universe systematically erases, reducing travelers to random particles scattered across the void. Recent discoveries of orphan stars, stars found in intergalactic space, torn from their home galaxies, revealed the violent nature of galactic interactions. These stellar exiles, drifting alone in the darkness, show what happens to matter caught between galaxies. They're cosmic warnings. Venture into the void, and you'll be stripped away from everything you know, lost forever in the emptiness. The quantum immortality thought experiment takes on new meaning for intergalactic travel. In quantum mechanics, every measurement creates branching worlds. Travelers might find that in most branches they die during the journey, but their subjective experience follows the unlikely branch where they survive. They might arrive at Andromeda, but they'd be the sole survivors from an infinite number of failed attempts across the multiverse. Observations of the Shapley supercluster, a concentration of galaxies 500 million light-years away that's pulling our local group toward it, show that galaxies aren't moving randomly. Large-scale currents govern galactic motion, and these currents might create cosmic weather patterns. Intergalactic travel would be like sailing against winds and currents we can't fully map, where getting lost means drifting for eternity. The cosmic censorship conjecture suggests that the universe hides its singularities, points where physics breaks down, behind event horizons. A similar principle might apply to intergalactic distances. The universe might actively prevent any observer from experiencing the truly strange physics that emerges at such scales, creating barriers that seem technological but are actually fundamental prohibitions. Recent studies of galaxy mergers show that when galaxies collide, most of their stars pass through without interaction, but the gas collides and heats up, triggering massive bursts of star formation. This reveals that galaxies are mostly empty space, but it also shows that the gas component, the interstellar and intergalactic medium, is where the action happens. Travelers would need to navigate not the stars but the invisible gas that fills the space between them. The particle horizon, the boundary of the observable universe, represents the maximum distance from which light has had time to reach us since the Big Bang. But this horizon is shrinking in co-moving coordinates due to accelerating expansion. Regions of space that we can see now will eventually move beyond our horizon forever. Andromeda will remain visible and potentially reachable, but most galaxies are already beyond the horizon of ever being reached. Quantum gravity effects, which we can't yet properly calculate, become important at the Planck scale, about 10 to the negative 35 meters. Over intergalactic distances, even if these effects are tiny at each point, they might accumulate into significant deviations from classical physics. Space-time itself might be foamy and chaotic at the smallest scales, and this quantum foam might create friction that prevents travel at the largest scales. The cosmological wormhole hypothesis suggests that the universe might be connected by shortcuts through space-time. But even if wormholes exist, they're likely to be microscopic, unstable, and would require exotic matter with negative energy to keep them open. The universe might tease us with shortcuts between galaxies while making those shortcuts fundamentally unusable. Recent observations of ultraluminous X-ray sources suggest that some black holes grow faster than theory predicts. If black holes can violate our expectations, what else might we be wrong about? Intergalactic space might be filled with intermediate mass black holes, too large to form from single stars, too small to be galactic centers, creating invisible hazards throughout the void. The multiverse concept, emerging from eternal inflation theory, suggests that our universe is one of countless bubble universes in an eternally inflating space. If this is true, then the barriers between galaxies within our universe might be echoes of the much larger barriers between different universes. We're trapped not just by distance, but by the fundamental structure of reality. Vacuum decay could occur if our universe exists in a false vacuum state, a local minimum in the energy landscape rather than the true ground state. A bubble of true vacuum could form anywhere and expand at the speed of light, destroying all structures it encounters. Intergalactic travelers face not just the journey ahead, but the possibility that reality itself could be erased before they arrive. The anthropic landscape, the idea that different regions of the multiverse have different physical constants, might mean that leaving our galaxy means leaving the parameter space where human life is possible. The physics that allows for our existence might be locally tuned, and crossing into regions with different parameters could be instantly fatal. Observations of the cosmic web's filamentary structure show that matter follows the densest paths, flowing along dark matter highways. But this also means that the voids, the truly empty regions, are becoming emptier as matter evacuates them. Crossing a void means traveling through space that's being actively drained of all matter and energy, regions that the universe itself is abandoning. The bootstrap paradox of intergalactic communication reveals another layer of our cosmic isolation. If we could somehow send a message to Andromeda, it would take 2.5 million years to arrive and another 2.5 million years for any response to reach us. By then, human civilization would have changed beyond recognition, if it existed at all. The beings who received our reply wouldn't be the ones who sent the original message. It's communication across geological time, where the conversation partners on both ends would be essentially different species. Recent advances in complexity theory suggest that maintaining organized information requires constant energy input to fight entropy. A spacecraft traveling for millions of years would need to continuously repair and refresh its data storage systems, its navigation computers, and its mission parameters. But the energy required for this maintenance would grow exponentially over time, eventually exceeding any power source we could conceive. The universe actively erases complex information, and fighting this erasure becomes impossible at intergalactic scales. The isotropy of the cosmic microwave background tells us that the universe looks the same in all directions, but this isotropy might be an illusion created by our local perspective. Some theories suggest that space has preferred directions at the larger scales, cosmic axes that would affect the propagation of matter and energy. Travelers to Andromeda might discover that space itself has a grain, like wood, and moving against this grain encounters resistance that builds over millions of light years. Observations of polar ring galaxies, where gas and stars orbit perpendicular to the main galactic disk, show that galaxies can have complex, three-dimensional structures. These warped configurations suggest that dark matter halos aren't simple spheres but twisted, prolate shapes that extend far into intergalactic space. Navigating through these invisible, irregular gravitational fields would be like flying blindfolded through a three-dimensional maze that changes shape as you move through it. The cosmic coincidence problem extends beyond dark energy. The ratios of fundamental forces, the masses of particles, and the expansion rate of the universe all seem fine-tuned for the existence of galaxies, stars, and life. This fine-tuning might necessarily create the isolation we experience. A universe where intergalactic travel was easy might be one where galaxies couldn't form stable structures, or where chemistry couldn't create complexity. Our cosmic loneliness might be the inevitable consequence of our existence. Recent studies of the local void, a region of space near us with unusually low galaxy density, show that we live near the edge of an enormous empty region. This void, spanning about 150 million light-years, affects the motion of nearby galaxies, including our own. We're not in a typical cosmic neighborhood, but at the boundary between dense and empty space. This position might protect us from certain cosmic hazards while making travel to other regions even more difficult. The cosmic microwave background's polarization patterns reveal details about the early universe's magnetic fields and the formation of the first structures. These observations show that magnetism has played a role in cosmic evolution since very early times. Intergalactic magnetic fields, invisible but pervasive, could create electromagnetic barriers that grow stronger with distance. Any spacecraft using electrical systems would face increasing resistance as it moved deeper into these cosmic magnetic fields. Quantum chromodynamics, the theory of the strong nuclear force, predicts that protons might not be perfectly stable. If protons decay, as some theories suggest, then over the millions of years required for intergalactic travel, the very atoms making up a spacecraft would gradually disintegrate. The hull, the electronics, even the atoms in travelers' bodies would slowly transform into lighter particles and energy. It's not just mechanical failure, but atomic dissolution that threatens intergalactic missions. The cosmic string network, if it exists, would create a web of gravitational anomalies throughout space. These one-dimensional defects, thinner than atoms but potentially stretching across the universe, would have gravitational fields that could deflect light and matter. A spacecraft might find its trajectory constantly modified by invisible strings, making precise navigation impossible. It would be like sailing through a sea filled with invisible cables that constantly alter your course. Recent discoveries of fast radio bursts repeating in predictable patterns suggest that some cosmic phenomena follow cycles we don't understand. The universe might have rhythms and periodicities at scales much larger than human timescales. Intergalactic travel could encounter cosmic weather patterns that operate on timescales of millions of years, storms, calms, and transitions that would be invisible to short-lived civilizations but deadly to long-duration missions. The holographic principle implies that the universe might be fundamentally two-dimensional, with the three-dimensional space we experience being an emergent property. If this is true, then traveling through space might actually be moving across a holographic projection. The barriers to intergalactic travel might exist in the holographic encoding rather than in physical space, making them impossible to overcome no matter what technology we develop. Observations of gravitational lensing by galaxy clusters reveal that dark matter forms complex substructures within larger dark matter halos. These subhalos, invisible but massive, orbit within the main cluster and could capture passing objects. A spacecraft traveling between galaxies might be snared by a dark matter subhalo, trapped in an orbit around invisible matter, doomed to circle forever around something it can't see or understand. The cosmic censorship hypothesis suggests that nature abhors naked singularities, points where physics breaks down without being hidden behind event horizons. A similar principle might apply to intergalactic travel. The universe might have built-in mechanisms that prevent any entity from experiencing the truly exotic physics that might exist in the deepest voids. Travelers might find themselves subject to effects that prevent them from observing or surviving conditions that would violate cosmic censorship. Recent measurements of the cosmic dawn redshift show that the first galaxies formed earlier than expected, when the universe was only a few 100 million years old. This rapid galaxy formation suggests that the structures we see today might not be permanent. Galaxies, including Andromeda, might be temporary arrangements of matter that will eventually disperse. By the time any spacecraft could reach Andromeda, the galaxy itself might no longer exist as a coherent structure. The quantum Zeno effect, where frequent observation can freeze quantum evolution, might operate on cosmic scales in ways we don't understand. The constant interaction of intergalactic travelers with cosmic radiation, neutrinos, and dark matter might create a macroscopic Zeno effect that prevents coherent change over long timescales. Travelers might find themselves frozen in a quantum limbo, unable to age, evolve, or even complete their journey. Dark photons, hypothetical particles that interact weakly with ordinary matter, could fill intergalactic space with invisible radiation fields. These fields, undetectable by current instruments, might become significant over the distances and timescales of intergalactic travel. Spacecraft electronics could be gradually degraded by dark photon interactions, creating failures that seem random but are actually caused by invisible cosmic radiation. The cosmic web's topology might be more complex than current models suggest. Recent simulations hint that the large-scale structure of the universe might have non-trivial topology, bridges, handles, and voids that connect in unexpected ways. What appears to be a straight path to Andromeda might actually follow a curved trajectory through higher dimensional space, making the journey much longer than geometric calculations suggest. Sterile neutrinos, if they exist, could decay into ordinary matter and energy over cosmic timescales. The intergalactic medium might be slowly accumulating matter and radiation from sterile neutrino decay, changing its properties in ways we haven't predicted. A spacecraft designed for travel through today's intergalactic environment might find itself in a very different medium millions of years into its journey. The cosmological constant's mysterious smallness might indicate that we live in a universe that's fine-tuned for observation rather than travel. A universe where dark energy was slightly stronger would have prevented galaxy formation. A universe where it was much weaker would have collapsed before complex structures could form. We might exist in a narrow parameter space that allows us to see other galaxies but prevents us from reaching them. Observations of the Bullet cluster, where two galaxy clusters have collided and passed through each other, show that dark matter behaves differently from ordinary matter during cosmic collisions. This separation of dark and ordinary matter might create complex gravitational fields in intergalactic space, regions where the gravitational effects don't match the visible matter. Navigating through these gravitational mirages could lead spacecraft far off course. The Wheeler-DeWitt equation, an attempt to quantize gravity, suggests that time might emerge from more fundamental quantum processes. At the scales relevant to intergalactic travel, the distinction between space and time might break down entirely. Travelers might find themselves in regions where temporal direction becomes ambiguous, where cause and effect relationships collapse, where the very concept of a journey loses meaning. Recent studies of cosmic inflation's eternal nature suggest that our observable universe is just one pocket in an infinitely expanding multiverse. If inflation is still occurring outside our cosmic horizon, then space itself might be expanding faster than light beyond our visible universe. Intergalactic travel would be like trying to reach the shore of an ocean whose edges are expanding faster than you can swim toward them. The Unruh effect predicts that accelerating observers see thermal radiation in what stationary observers consider empty vacuum. For spacecraft accelerating toward Andromeda, the vacuum of intergalactic space would appear to glow with thermal radiation. The faster they accelerate, the hotter this radiation appears. At the accelerations required for reasonable travel times, the vacuum would appear as hot as the Sun's surface, making the journey impossible. Cosmic microwave background anomalies, deviations from perfect isotropy, might indicate that our universe has large-scale structure we don't understand. The cold spot, a region where the microwave background is unusually cool, might be evidence of a supervoid or even a collision with another universe. Such anomalous regions could have different physical properties that make them impassable barriers to intergalactic travel. The black hole information paradox, still unresolved despite decades of research, suggests that information might not be preserved in extreme gravitational environments. Over intergalactic distances, the cumulative gravitational effects of billions of stars and dark matter concentrations might create information-destroying environments. The memories, purposes, and identities of travelers might be gradually erased by the universe's information processing limitations. Recent observations of gravitational wave echoes suggest that black holes might not have the smooth event horizons predicted by general relativity. If spacetime has quantum structure at small scales, this structure might also affect the large-scale geometry of intergalactic space. The smooth spacetime we assume for navigation calculations might be an approximation that breaks down over cosmic distances, creating navigation errors that accumulate catastrophically. The cosmological lithium problem, the discrepancy between predicted and observed primordial lithium abundance, might indicate unknown physics in the early universe. If we're wrong about something as fundamental as Big Bang nucleosynthesis, we might also be wrong about the stability of matter over cosmic timescales. The atoms making up intergalactic travelers might undergo unknown transformations that we haven't predicted. One often overlooked aspect of intergalactic travel is the immense difficulty of stopping once you arrive. Most discussions focus on the energy required to accelerate a spacecraft to relativistic speeds, but the laws of physics are symmetric. To slow down upon reaching Andromeda, you would need to expend essentially the same amount of energy as you used to speed up. This creates a devastating fuel problem. You must carry enough fuel to accelerate to near light speed, plus enough fuel to decelerate at the other end, plus fuel to carry that fuel. The tyranny of the rocket equation means that the required fuel mass grows exponentially with the desired velocity, making even a one-way trip with a stop practically impossible. The shielding required for intergalactic travel presents a paradox that current engineering cannot solve. To protect against impacts with interstellar dust and high-energy radiation, a spacecraft needs thick, dense shielding, perhaps meters of lead or water. But this mass makes the spacecraft exponentially harder to accelerate. Conversely, if you strip away the armor to make the ship light enough to move fast, you leave the crew vulnerable to even the tiniest grain of dust, which would strike with the force of a tactical nuclear weapon at relativistic speeds. You are caught between the impossibility of moving a fortress and the lethality of traveling in a tin can. Andromeda itself is not the peaceful destination we often imagine it to be. Unlike our relatively quiescent Milky Way, Andromeda is a cosmic predator. Observations show it has a violent history of cannibalizing smaller galaxies, and it is currently in a state of turmoil. It possesses a double nucleus, two bright cores in its center, which suggests a complex and potentially chaotic gravitational environment. Arriving in such a system wouldn't be like parking in a quiet harbor. It would be like sailing into a hurricane. The gravitational disturbances from past mergers could send comets and asteroids careening through any region we tried to settle, making the destination just as dangerous as the journey. The cosmic dust lying between the galaxies poses a more severe threat than simple radiation. While the intergalactic medium is incredibly thin, it is not perfectly empty. Over a distance of 2 million light-years, a spacecraft will inevitably encounter clouds of gas and dust. At 10% of the speed of light, a microscopic dust particle hits with the energy of a bomb dropped in the Second World War. At 50% of light speed, that same particle releases energy comparable to a tactical nuclear explosion. The erosion of the spacecraft's leading edge would be continuous and catastrophic, sand blasting the hull into oblivion long before the galaxy is reached. Navigation becomes a nightmare once you leave the familiar confines of the Milky Way. On Earth, we navigate by the stars. Within our galaxy, we use pulsars, rapidly spinning neutron stars that act as cosmic lighthouses. But once you exit the Milky Way, these reference points either disappear or become indistinguishable from background noise. You would be sailing in a featureless void with no landmarks, no GPS satellites, and no way to determine your precise position. A tiny error in your initial trajectory, just a fraction of a degree, would cause you to miss Andromeda by millions of light-years, drifting forever into the empty dark. The Kardashev scale, a method of measuring a civilization's level of technological advancement based on energy usage, puts our current limitations into stark relief. We are not even a Type 1 civilization yet, unable to harness all the energy available on our own planet. A Type 2 civilization could harness the total energy of a star. A Type 3 civilization could control the energy of an entire galaxy. Even for a hypothetical Type 3 civilization, harnessing the entire output of billions of stars, the energy budget for intergalactic travel would be staggering. The distances are so vast that they strain the capabilities of even godlike civilizations, suggesting that the barriers might be absolute regardless of technological advancement. The heat generated by the spacecraft's own systems presents a thermodynamic catch. In the vacuum of space, there is no air to carry heat away. Thermal energy can only be radiated away as infrared light. A spacecraft carrying a nuclear reactor, life support systems, and powerful computers would generate immense waste heat. Over millions of years, dissipating this heat without melting the ship requires radiator fins that would be hundreds of square miles in area. These fragile structures would be the first thing torn off by collisions with interstellar debris, leading to a rapid overheating and the death of everyone aboard. Consider the breakdown of human culture and language over such timescales. The journey to Andromeda would take thousands or millions of generations. The English language, or any language we speak today, would be unrecognizable to our distant descendants within a few thousand years. Cultural norms, scientific knowledge, and the very purpose of the mission would mutate and distort over time. By the time the spacecraft arrived, the descendants of the original crew might have no understanding of who built the ship, where it came from, or why they are there. They would be a lost tribe in a metal can, worshipping the machines their ancestors built. The concept of the Great Filter in the Fermi Paradox suggests that there is some evolutionary barrier that prevents civilizations from becoming spacefaring empires. Perhaps the filter is not a biological or political collapse, but the simple physics of intergalactic space. The energy requirements, the timescales, and the biological hazards might act as a universal dam, trapping every intelligent species within its home galaxy. We might be looking at the solution to the Fermi Paradox when we look at the gap between the Milky Way and Andromeda. Everyone is stuck at home. The cosmic web structure, the vast filamentary network of matter that connects galaxies, might actually work against intergalactic travelers. While filaments contain more gas and potential resources, they are also gravitational highways that attract dark matter and dense clumps of matter. Traveling along a filament might mean dodging denser regions of gas and stronger gravitational fields. Traveling across the voids, conversely, means facing the accelerating expansion of space that pushes you backward. The universe's macrostructure offers no easy route. It is a maze designed to keep you within your local sector. Recent simulations of galaxy formation show that galaxies like Andromeda and the Milky Way are surrounded by massive halos of hot gas, the circumgalactic medium. These halos extend hundreds of thousands of light-years into space. To actually reach Andromeda, you wouldn't just cross the void, you would have to punch through this wall of superheated plasma surrounding the galaxy. This gas is so hot that it emits X-rays, and flying through it at high speeds would be like flying through a furnace. It would act as a braking mechanism, stripping away velocity and heating the spacecraft to the point of destruction before it ever got close to a star. The psychological concept of the overview effect describes the cognitive shift astronauts experience when seeing Earth from space. Imagine the cosmic isolation effect experienced by travelers in intergalactic space. For millions of years, the only visible objects would be the distant, unchanging points of stars in other galaxies. There would be no sunrise, no changing seasons, no comets, no meteors, just an eternal, static night. This sensory deprivation could lead to a profound psychological collapse, where the human mind, evolved for a dynamic environment, simply shuts down under the weight of eternal monotony. Even the fundamental constants of nature might not be constant over such vast distances. While physics assumes that the speed of light or the gravitational constant is the same everywhere, some theories suggest that these constants could vary slightly across the universe. As a spacecraft travels deeper into the void, it might drift into regions where the laws of physics are subtly different. Nuclear reactions might slow down, atomic bonds might weaken. The very machinery of the spacecraft, built on Earth's physics, might cease to function in a region of space with different fundamental rules. The logistics of storing information for millions of years is another hurdle. Every hard drive, every book, every DNA sample degrades over time. To preserve human knowledge for the duration of the trip would require an active, powered system of error correction, constantly refreshing the data. But a power system that lasts millions of years is a contradiction in terms. By the time they arrived, the travelers might know less about Earth than we do about the Stone Age. They would be strangers to their own history, carrying a corrupted database of a world they would never see again. The Poynting-Robertson effect, which causes dust particles in a solar system to spiral into the star, has a relativistic counterpart that could spell doom for intergalactic travelers. As a spacecraft moves through the radiation fields of the universe, it experiences a drag force. This drag is negligible at low speeds, but as you approach the speed of light, it becomes significant. It acts like a cosmic friction, constantly trying to slow you down. The faster you go, the harder the universe pushes back, creating a terminal velocity that might be far lower than the speed of light. Consider the problem of biological reproduction in a closed system. A generation ship is a closed ecosystem. Over thousands of years, genetic drift would reduce the genetic diversity of the population. Inbreeding depression would become a serious threat, leading to a population too weak to survive the harsh conditions of a new galaxy. They would arrive physically compromised, their immune systems unable to cope with even the simplest alien bacteria, assuming any could be found. The sheer scale of time required for the journey means that the universe itself would change dramatically while the travelers are in transit. Stars would be born and die, galaxies would merge. The cosmic background radiation would cool further. The destination they aimed for might not exist when they arrive. Andromeda itself might have collided with the Milky Way by the time a slow ship gets halfway there, turning the destination into a chaotic merger zone that bears no resemblance to the target they locked onto millions of years ago. Finally, there is the issue of causality and free will. If the travelers are isolated from the rest of humanity for millions of years, their actions have no consequences for Earth, and Earth's actions have no consequences for them. They become a separate reality, a bubble of space-time disconnected from the causal chain of human history. In a very real sense, they would no longer be part of the human universe. They would be a new species adrift in a sea of night, effectively alone in the cosmos, serving as a testament not to human ambition, but to the impassable boundaries of the physical world. But if you want to know how far we can currently travel across the cosmos, check out this video at the left side of the screen. In this video, we explore the true limits of interstellar travel, time dilation, and the mind-blowing physics that could make journeys to distant stars possible within one human lifespan. See you there.